this video is going to be about something called Gauss's Law. So one thing that we've learned hopefully by this point in the class here is that whenever we have a charge, the charge itself always produces an electric field. In other words, just having a charge in existence, it fills space all around it, fills the entire universe for that matter with its electric field lines. So charges in a sense are sources of electric fields. And we've seen several cases now. We have the classic point charge, we have a line of charge, we have a ring of charge. They all produce their own variety of electric field that has a different look and different direction and different equation relative to the object itself. And what we've done thus far in order to calculate the electric field, or in other words, to figure out what is the electric field at this point, or at this point, or at this point, or somewhere along the axis of a ring, is we use a rather painful procedure here that uses a lot of calculus. In particular, we took the equation for the point charge here and we made a differential form of it. So instead of E is kq over r squared, we did dE is k dq over r squared. And went through a lot of headache of filling in all sorts of things for dq's and r's and things. And our last step was always to do an integral. Now, although this technique is very difficult here, particularly because of all the calculus that it involves, it's a very robust technique. In other words, it works every time. There isn't a single charge distribution that you can't set this up for and end up doing an integral and do it. Now, it may be that you can't do the integral yourself, or in calculus class you haven't done it, or maybe the integral is even impossible, but it still always ends with doing an integral, which, for example, computers are really good at doing these days, even if it just gives you a number, not an analytical expression. So what Gauss's law is about is another way of calculating electric field in a nutshell. So we'll have some charge distributions once again, and we'll still be curious about what the electric field is, and we'd like to calculate that electric field. And Gauss's law can do that for us. I've written Gauss's law down right here. You probably have a copy of it in your textbook, or you can find the equation also types in on Wikipedia. See some various elements about it. In particular, it involves two, not just one integral, and there's a ring around the integrals. We'll talk about what those mean here. Here's the electric field that we'd actually like to solve for here. But one thing about Gauss's law, it's a bit foreboding. It has its own difficulties as well. I would say the mathematics is not as difficult as this technique that works all the time, but it has its issues as well. In particular, if you look at it here, like I said, you have two integrals with a ring around it, and the electric field that you want like to solve for is sitting right in there. It's a vector, but it's buried right in a dot product, and to make it even worse, it's inside of an integral. So you really can't just pull it out and solve for E directly. Like you just can't take this in one line, go E is equal to something, and have your answer. A bit of work has to be done. And so this integral is all equal to something, and in particular it's equal to Q sub E, which I'm denoting here as this E means enclosed. So I'm always going to refer to it as a charge enclosed, and of course the epsilon is just some constant here from the front cover of your book, which is 8.85 times 10 to the minus 12. You can look that up. So just a constant in there. So there are some considerations that you have to think about before using Gauss's law. And already we can sort of attack it just a little bit here. What do I mean by charge enclosed? Well, enclosed by what, or who's enclosing what, or what's the enclosed happening here? Well, you have this ring here around the integrals. And what the two integrals mean, remember one integral like this means sort of a 1D integral. It might be an integral on a line or something like that, one-dimensional space. But when you have two integrals like that, that's definitely a two-dimensional integral, and that sort of refers to an area. We don't need it here right now, but three integrals, of course, means 3D, and that would refer to a volume. So fortunately for us, Gauss's law just has two integrals, and it refers to an area. So if you look up here at the two integrals, they are talking about an area, but the fact that the area has a ring around it here, in other words, it isn't just two integrals like that, it's some integrals, and that is definitely a ring around those integrals like that. This also means, or actually not also, but does mean a closed area. So Gauss's law is something that always deals in closed areas. So you can't just choose something like a square like this, because a square isn't closed. There's all this sort of room up here and up here. Or you can't just choose something like a circle or a disc like this, because this isn't closed either. There's all this space around it that isn't enclosed by the area. You have to choose something like a sphere like this, because a sphere is an enclosed area. There is definitely a portion of space that's inside the sphere, and there's a portion of space that's outside the sphere, and Gauss's law will be concerned with what's inside of that sphere. This is a closed surface here. So the first two here, just a square or circle, aren't going to work, but the sphere will work. That is a closed area here. The other type of closed areas we have are something like a cylinder like this. A cylinder is also a closed area, because there's definitely regions of space that are inside the cylinder. That's what Gauss's law will be concerned with. And there's spaces that are outside the cylinder that we're not going to care about. But the point is that this encloses some space. The last one that you probably will use in Gauss Law is a cube like this, or rectangle like this, is also something that's an area that has an enclosed space here. In other words, you can say something is inside the box or outside the box. So it turns out as you work your way through Gauss's law, these types of shapes are probably the only three you'll ever encounter, and the reason being is because they're simple geometries that have enclosed areas, or they enclose some space. And that's exactly what Gauss's law calls for. It says, hey, if you can provide me with a surface that's closed, that's what that ring means right there. So a sphere, a cylinder, or a box like that, sphere, a cylinder, or a box like that, that's closed like that. And furthermore, if that closed figure encloses some charge, that's the key thing about Gauss's law. If you can get an enclosed shape that encloses some charge, then Gauss's law can work for you right here. So that's sort of what it means here. The two integrals here with the ring around it means an enclosed object. And I'm giving you about the only three you're ever likely to encounter here. And so these things tie together here because now the Q enclosed, the charge enclosed here, is that's enclosed by this object right here. So if you can sort of put this together here, if you can look at your problem and go, yeah, I can identify a closed object that encloses some sphere, then likely Gauss's law can work for you. But there's one more very important part about Gauss's law in its meaning here, and if we go back, all right, so we sort of discussed the integral and what that ring means, and that the closed surface has to enclose some charge. That sort of brings the two sides of this equation together. But there's one more element in here, which is this dot product in here, which can be sort of a bit tricky as well. So why don't we just talk about that now, and that'll sort of end our introduction to Gauss's law. So we're trying to work up the conditions here for what Gauss's law means and how we might use it. So okay, we identify a closed shape. We identify that it can enclose some charge. What else do we need here? So let's just erase some of this stuff right here and just talk about that dot product for a minute here. We'll sort of leave Gauss' law up there as is. There it is. Looks like, well, let's go ahead and rewrite it to make it a bit neater, maybe a bit bigger here. So Gauss' law in its glory here. There's a closed integral of E dot ds is equal to the enclosed charge divided by epsilon. Okay, here's Gauss' law. And what we just discussed then is that the double integral with a ring around it means an enclosed shape. And the enclosed shape is going to enclose some charge. So these two things sort of go hand in hand. But the last sort of requirement or use for Gauss's law is that you have to worry about this dot product in here. This is a dot product. And probably the easiest way to handle this dot product is to go ahead and expand it in terms of some scalar variable. So E dot ds then is going to be E times ds times the cosine, say, of phi. And phi here is going to be the angle between E and ds. That's just the way the dot product works. You can look that up in your physics book or your calculus book for a little bit more information on that. So if you have this going, you see we're already making a bit of progress because now by writing it this way, we've broken E out of its vector form, now the dot product, so it looks a little bit more like something we can solve for. However, you have to remember where it exists. It initially exists inside its integral. So even though we've broken it out of the dot product, E dot ds, so we'll just sort of write it like this because that's sort of what this becomes by breaking that dot product out. You have to be a bit careful now in how you use Gauss' law because remember, you're integrating over ds, and ds ultimately is going to be it's going to be the surface of your object. And by the way, that object is usually called your Gaussian surface. So we can start referring to that way. The ds is your Gaussian surface. But remember that as the integral visits the surface, goes over all points of the surface. That's what integrals typically do. So say we had a sphere like this here that looked like this. What that double integral does is it forces the mathematics to visit every single point along that sphere here, here and here and here and here and here and here, all these points in probably a better order than I'm drawing them here. But the point is that you visit all the points here, and then when you have something like that, even all the points in between now. That's what calculus does. It gets in between and looks at all those little differentials in there. And you keep doing that until you've mapped out the entire surface area of the object that you're working under right here. That's the way Gauss' law works. And so if you're doing that, you have to be a bit careful now that this angle between the area and the electric field is something that can be handled properly. What do I mean by that? Well, remember what is the angle of an area? Well, if you have a little slab of this sphere, maybe a little bit of patch that looks like this, so this patch might very well be this little patch right here on the sphere, the angle of this area is always a normal vector which points outwards and is perpendicular to the surface area. So that's sort of the angle of this area. That's the direction of ds right here. But now you have this E here, which is your electric field. So the issue is like if maybe you have your electric field looks like this and your normal looks like this. Well, what is the cosine of the angle? What is the angle between them? Well, in this case here, phi is just 0, and so the cosine phi is just going to be 1. It makes it nice and easy like that. You can have other cases where maybe the area sort of looks like this. This might be just a little patch of one of the points you might visit here, and the normal to the area might be like that, but the electric field might point over this way. And in a case like this here, we get phi is equal to 90 degrees. And in this case, the cosine of 90 degrees would just give 0, so it would just make the whole integral go away. The problem that you'd run into with Gauss's law is if the angle of the normal and the angle of the electric field kept changing all the time relative to the position that you're integrating over. So for instance, say you chose something poorly and in one instant your normal was up like this and your electric field was up like this, and you say, oh, it looks like I'm on the right track. They're in the same direction. The angle is 0 degrees. It can work out. Then the very next sort of area of space, maybe the normal is like that and the electric field is like this, and maybe you don't even know the angle. Then maybe the normal is like this and the electric field is down like this, and the area keeps changing like that. Or maybe even the normal jumps all the way over here because of some irregular shape. The electric field is down like that. And so all I would say about these cases here is what on earth are you going to put in for phi in some of these really wild cases here like this? And the answer to that question is try to avoid the wild cases altogether. So what you always want to do with Gauss' law, and that's sort of the last requirement here, you always sort of like to, we'll sort of write it out here. Choose a Gaussian surface that matches, the E field direction. In other words, you always want to try to go for something like matches. You always want to sort of go for a 90 degrees or a 0 degree angle. Those are the only ones that are going to make the problems tractable at all. So that's a restriction of Gauss's law, is that it's only going to work in highly symmetrical cases. Highly symmetrical cases. And again, that is unlike the very brute force but robust technique that works all the time. Gauss's law only works in highly symmetrical cases. And why is that it only works in highly symmetrical cases? Because the only Gaussian surfaces that you really have at your disposal that enclose some area, again, are that sphere, the cylinder, or the cube. So you're really forced with the Gauss's law, you can only actually use it for electric fields that are sort of cylindrical, spherical in nature, cylindrical in nature, or sort of cubical in nature. But we have a lot of systems like that, because what does the sphere look like? It looks a lot like a point charge. So we can imagine putting a point charge in there, and we see all these electric field lines sort of going out, and we see it matches the sphere very nicely. In fact, what do I mean by match the sphere? Well, these pink lines are the electric field lines, and if I draw some little black lines on the sphere, that's a normal. That's a normal. That's a normal right here. Even down here, there's a normal right there. So see, all the normals match up the electric field lines very nicely. In fact, make a 0 degree angle, making this dot product in Gauss' law very easy to evaluate. And what does the cylinder look like? Well, it looks like a system we've seen many times. It looks like a line of charge. The line of charge has electric field lines going out in all directions like this. Let me put a few arrows on there. Like this and like this and like that, going in all directions. Of course, the normals to the Gaussian surface look like that. And like this, the normals always match up to those arrows very nicely like that. In fact, another 0 degree case. And what sort of matches up with a cubical surface like this? Well, we can imagine putting a sheet of charge in there. Remember, the sheet of charge looks like a big bed sheet full of charge on it like that. And the electric field lines are going out in all directions like this and like this. So there's the arrows on there like that. And what you notice also, once again here, is the normals also match up very nicely with those electric field lines like that. Look at all these normals in there. It looks up very nice. And on the sides, the normals are going to look like this on that cube, but that's okay. The angle is very predictable in there as well. The electric field line might be up, but the normal is at 90 degrees, and that's okay. A phi of 90 degrees means the cosine 0, the integral just becomes 0 now, so this is happily handled as well. So those are your three things about Gauss's law here. We took a look at the integral in this video here and saw that there's a closed surface that encloses some charge. There's just a constant in there, and you have to choose a Gaussian surface that very well matches the symmetry of your electric field configuration, or you won't be able to use it. So there's sort of your introduction to Gauss's law. There's going to be another series of videos that you can find that come after this one here that will talk to you very explicitly about how you handle the left side here. We'll just call it the left-hand side. That's sort of usually handled by itself. And how are you going to handle the right-hand side? Because that can be a bit tricky. So there'll be 2 more videos on that, and probably 1 more that illustrates the use of Gauss's law with some simple cases.